great. Thank you very much. Thanks for giving me the opportunity to speak. So yes, I'm talking about embedding things into products of trees. And here, so I'm thinking of a product of trees as being some kind of model geometry for the space or a group. And the idea is that if this model geometry is something you understand the geometry of well, and so if you can embed something inside it, then that's supposed to be an informative thing. So but for hyperbolic groups, maybe the best kind of model geometry comes from a famous result of Bonk and Schramm. From 2000, and they proved that every hyperbolic group can be quasi-asymmetrically embedded in the standard hyperbolic n space for some n. So if G is a hyperbolic group, then G can be quasi-asymmetrically embedded in the standard hyperbolic n space. So I think this theorem's really nice. Here, kind of the model rank 1 space receives all of the coarse rank 1 groups. The only thing that you could argue is maybe not satisfying about this is the value of this n, which I didn't say anything about. But the value of n in this theorem depends not just on the dimension of the hyperbolic group, it depends on how the balls in the hyperbolic group grow. So if the balls grow faster, then you need a larger n for this statement to be true. So the dimension of this hyperbolic space does not directly reflect the dimension of the hyperbolic group that you started with. And if you want a model geometry that does reflect the dimension of the group, that's when a product of trees comes in. So there's a different result. It comes from a few different works, but kind of the pieces are all in the end put together by Boiarlo and Lebedeva in 2008. And they proved that if G is a hyperbolic group, then G can be quasi-asymmetrically embedded in a product of trees, and it's the correct number of trees. So G can be quasi-asymmetrically embedded in, so product of trees, and the number of trees is 1 plus the dimension of the boundary of G. So yeah, when I say dimension here, I'm just meaning the topological dimension of that topological space. And 1 plus the dimension of the boundary, if G was torsion-free, this would be the same as the cohomological dimension of G by best being n mass. So this is the correct number of, this is like the correct dimensional thing. And yeah, so like I said, this combines a couple of different works, and the actual construction of the embedding, given some other things, comes from work of Boiarlo. And I thought that I would just give a sketch of how that construction works. It's not actually going to be relevant to the things I talk about afterwards. I just think it's a nice idea, so I wanted to describe how that goes. And I'm just going to do it in the case where the group is quasi-isometric to hyperbolic 3 space. So I'm just describing a quasi-asymmetric embedding of hyperbolic 3 space into a product of 3 trees. And then if you want to do this in general, lots of things will be harder. But let me just sketch this for H3. So start with H3. Its boundary is the two-sphere. So boundary of H3 is two-sphere, which I'm going to think of as the plane union a point. And just to make my own life easier, I'm just going to forget about that point and just draw pictures in the plane. It's to be understood that these things are really happening in the sphere. Okay, so I've got the sphere, which I'm going to think of as the plane. And you can tile the plane by bricks. So this is the kind of standard picture that you see that shows that the plane is two-dimensional. I'm going to tile it by bricks that have the same size. And I can color these bricks with 3 colors such that any 2 bricks of the same color are disjoint from each other. Okay? So I get a covering of the plane. So I get a covering which I'm going to call U1, and it's composed of 3 parts. The first color, the second color, and the third color. Okay, so U11 consists of all of the bricks labeled 1. Okay. Now I can do the same thing, but with smaller bricks. I'm just covering the plane by these bricks. I can do it just with a smaller fixed size of brick. Okay, so now repeat with smaller bricks. Oh yeah, I forgot to use the thing. To get U2, which again decomposes into 3 families of bricks. Okay, but I'm going to do this in a particular way. So if I zoom in on, here's the old big picture that I had, and the next set of bricks that I take, so this was colored 3, 1, 2. I'm going to do this in such a way that when I take my smaller bricks, if I look at a smaller brick colored 1, and I take a bigger brick colored 1, then either my smaller one is contained in my big one, or it's disjoint from it. Okay, this second covering by smaller bricks is kind of aligned with the first one that I took. So in such a way that if V is in U21 and W is in U11, then either V is contained in W or V is disjoint from W. Okay, so now I've got 2 coverings of the boundary of H3, and the second one is smaller than, but aligned with the first one. And I repeat this, and I get a sequence. I get UK, which is UK1 union UK2 union UK3. Okay. Now I'm going to use those to make 3 trees. So the 3 trees will come one from the UK1s, second from the UK2s, and the third from the UK3s. So now make 3 trees, T1, T2, T3, and they're going to be rooted trees. So yes, so T1 has a vertex called Vn for each V in UN1. Okay, so for each element, for each brick in one of my covers at each level, I take a vertex. And then edges correspond to minimal containment. So maybe here is one of the bricks labeled number 1. And then here's a smaller one. It's got some level 2 one-colored bricks inside it and some outside it. And then if I draw the level 3, so this is in the first level. This is in the second level. And then I've got some third level bricks, which are smaller again. So in my rooted tree, I'll have the root, which I'm going to think of as corresponding to the entire boundary. Then I've got some level 1 vertices. In here I've drawn 4 of them. Okay? They're all attached to the root, because I'm thinking of the root as the entire boundary. Now I've got some level 2 vertices. And some of these are contained in level 1 vertices, and that's a minimal containment. So I've got some like this. But some of them are not. So the smallest thing that's contained in is the root. So I get some tree like this by adding edges in this way.
What does this rule say about?
This rule says that the thing that I did there actually makes sense to do. It tells you that the minimal containment thing actually can, well.
But you, like, in the original thing of level 1, you had like a lot of ones, but you only choose one for the root.
So, sorry, the root is kind of corresponding to U0, which consists of a single set, which is the whole boundary. Yeah.
But then, so it's like, has infinitely many. It's compact.
Yeah, so it's compact, so there's finitely many at the first level. Yeah, that's one way where I cheated by drawing it in the plane.
Okay.
But you're right, because although I drew this edge as longer, all of these edges are actually going to have length 1. So the root does have infinite valence. Yeah. It's just that it's only got finite valence coming from each level.
How do you pick these scales? Like, there are so many options to go to the smaller covers. Do you go dietic, or how do you?
So I think that as long as the next scale is something like a sixth the size of the... There's some care in choosing... Any small enough scale will work, and then how small it needs to be is dependent on some parameters that come with the setup and depend on which boundary you're looking at. But so it's kind of, I'm not being very precise here, but this is just the picture. So so you get this sequence of covers. From the sequence of covers, you build a tree. So doing this for each of the 3 colors, we get 3 trees. And so now I just need to say how you map hyperbolic 3 space to this product of 3 trees. And for that, I'm again not going to be very precise. But the basic idea is to look at shadows. So to map H3 to T1 times T2 times T3, look at shadows. So here's H3, and I pick some base point. And now, if you give me some point x here in H3, I'm going to draw the unit ball around it. And then I'm going to look at all of the geodesics that go through that ball. And that gives some shadow in the boundary. So in order to map to T1, so a map from H3 to T1 times T2 times T3 is made of 3 maps, 1 to T1, 1 to T2, 1 to T3. So I need to say which vertex of T1 this point here gets mapped to. Well, I look at the shadow, and I find the smallest one-colored set in the boundary that contains it. That defines some vertex of this tree, because the vertices of the tree came from the elements of the covers. And I just map this point to that vertex in that first tree. And then I do the same with the second tree, and the same with the third tree. And then one can show that that map defines a quasi-isometric embedding. Okay. Yeah, okay, yeah. Yeah, let me leave that there. Okay. Okay, I'm not going to draw a box after that. Yeah, anyway, so yeah, like I said, that's not actually relevant for what I'm going to say afterwards. I just think it's kind of a nice argument. So yeah, anyway, so hyperbolic groups can be quasi-symmetrically embedded in the correct number of trees. And in fact, by an elaboration on this and using dark magic, that funnily enough also involves the Morse 2.0 sequence that Pierre-Emmanuel talked about, this theorem can be improved. This was done by Boyarlo, Dranishnikov, and Schroeder in 2007. So I'm not sure what's going on with the publication dates here. But they proved that if G is a hyperbolic group, then G can be quasi-symmetrically embedded in a product of the same number of trivalent trees. So the trees that we had here were infinite valence, but you can actually do it with all the trees being regular trees. So equivalently, the hyperbolic group embeds in, quasi-symmetrically embeds in a product of free groups, the correct number of free groups. Yeah, so, okay, very good point. It's not relevant at all, essentially. Yeah, nothing I said here was actually about groups. You need, sorry? Yeah, it needs to be a hyperbolic space with some control on how the balls grow at some scale. So, yeah, Bonk and Schramm call it bounded growth at some scale. But yeah, so there's some slight conditions so that it doesn't go completely out of control, but yeah, essentially all of these things work for hyperbolic spaces. There's no group action involved in any of this, and in a sense there couldn't be, because if you have a hyperbolic group with property T, it's not going to act on a product of trees. So you can't actually get an action in some of these statements. So yeah, it's all kind of metric stuff. Okay, so that's the situation for hyperbolic groups. Outside of hyperbolic groups, there's not, well, in most cases, there's not really that many results. There's a there's a result of Mackay and Sisto that says that if you're relatively hyperbolic and the pieces the peripherals quasi-isometrically embed in a finite product of trees, then the relatively hyperbolic group does as well. And there's also a result of David Hume that says that mapping class groups can be quasi-isometrically embedded in a finite product of trees. That uses the projection complex machinery of Vesvina, Brombo, Fujiwara. And so both of these essentially rely on the stuff for hyperbolic spaces. But there's another situation, another setting where you can make lots of embeddings in products of trees, and that's cat-zero cube complexes. And you can do that with the following lemma, which I'm just going to say it's well known. I'm not sure where the exact, there's some version of this without any of this language in paper of Dranishnikov and Januszkiewicz from the 90s, and then it appears in a PhD thesis of a student of Graham Niblo and 8 years later or something. But yeah, anyway, it seems to be something that people know about. And the limit is if X is a cat-zero cube complex, such that the hyperplanes of X can be n-colored, such that whenever you have two of the same color, they don't cross, then you can isometrically embed in a product of n trees. Okay, and if the coloring of the hyperplanes was an equivariant coloring, then it's an equivariant isometric embedding in a product of trees. And okay, I was originally going to give the arguments of this because it's not so long, but I think in the interest of time I won't. But maybe I won't write it. Maybe I'll say it. But okay, the point is you've got your cube complex and you've colored the hyperplanes. Look at the hyperplanes of one color and consider just those hyperplanes on X. You've got a wall space. You've got the cube complex X with a set of walls. And with that wall space, you can do Segev's construction and you get a dual cube complex. And because none of those hyperplanes crossed, that dual cube complex is a tree. So doing this once for each color, you get n trees. And you also get, so when you look at the hyperplanes of one color, you also get a natural map from the cube complex to that dual tree. When you have a point in the cube complex, you just look at which side of all of those hyperplanes it was on, and that gives you a point in that tree. So the way you produce those trees with the Segev construction also gives you a map to their product, and the reason it's an isometric embedding is just the distance between vertices is the number of separating hyperplanes. And so you split them up into different colors, you still got the same number in the codomain as you did in the domain. So that's, yeah, okay. Yes, right. Yeah, yeah. In some sense, most of the time, this is going to be locally infinite. Yeah. Okay, so one situation where you can apply this lemma is for right-angled Artin groups. So corollary, if gamma is n-colorable, then the right-angled Artin group A gamma isometrically embeds in a product of n trees. And yeah, as Miko pointed out, these trees are most of the time going to be locally infinite trees. Okay, and turns out that also in the setting of right-angled Artin groups, dark magic is also effective. And there's a theorem of Alina Rule from her PhD thesis, which says that if gamma is n colorable, then the corresponding right-angled Artin group quasi-isometrically embeds in a product of n finite trivalent trees, or equivalently in f2 to the n. Okay. Right. But compared to what I was saying before about hyperbolic groups, there the dimension in the number of trees that you needed was the dimension. But here, the dimension of the right-angled Artin group is the size of the largest clique in gamma, which in general is going to be less than the coloring number. There's this classic construction of Michalski that shows that you can have graphs with no triangles, but arbitrarily large chromatic number. So the number of trees involved here is maybe much larger than the dimension. So a reasonable question you could ask is, do you really need that many trees? And so that brings me to the following statement with Shaked Badr and Oussama Bensaid. So we showed that if a right-angled Artin group A gamma can be quasi-asymmetrically embedded in a product of two trees, then gamma had to actually be two colorable. So it's saying, yeah, so it's going in the other direction to this. So in particular, all of those Michalski graphs cannot be quasi-symmetrically embedded in a product of two trees. Even just the rag on a pentagon can't, because you can't two-color the pentagon. And so, yeah, so that's in the two-dimensional case. And then we also have a result in higher dimensions, but an extra assumption is needed, although I won't get into what that assumption is. So under an additional hypothesis, if an n-dimensional right-angled Artin group quasi-symmetrically embeds in a product of n trees, then gamma is n colorable. This result is part of a larger work about embedding right-angled Artin groups into each other, because yes, this product of free groups here, right-angled Artin group, product of trees, product of infinite rank free groups. Shaked's going to talk much more about that tomorrow. Okay. So that's something about right-angled Artin groups. But oh yeah.
Is that emphasis on the embedding or on gamma?
It's on gamma. Yeah. Yeah. It's something about cliques being an intersection of enough cliques and that kind of thing. Yeah. So as Sam pointed out, none of the things about hyperbolic groups were really about groups. They were all about spaces. So what about cat-0 cube complexes more generally? What can be said about those? So for example, if I have a cat-0 cube complex, does it always isometrically embed in a finite product of trees? Well, by the well-known lemma, that's the same as saying, if you have a cat-0 cube complex, can you always finitely color the hyperplanes? Okay, but the answer to that is no, because if you take any graph, you can build a cube complex where that graph is the link of a vertex. So then if you take a graph that can't be finitely colored, then that cube complex will not be embeddable in a finite product of trees. So any graph can appear as the link of a vertex in a cat-0 cube complex. But the way that I did that by making it appear as a link, if I take a graph that requires many colors, well, that graph has to have many vertices. So this cat-0 cube complex that is appearing as the link of a vertex in, it's not, well, the easiest way of doing this would be it's not even locally finite, not a locally finite cube complex. You could work a bit harder and make it so it's not uniformly locally finite. But then having large chromatic number forces large vertex degree. So a question you could ask is, well, if I just bound the degree of a vertex in my cat-0 cube complex, does that get rid of this issue? If I have a cube complex where the vertices all have bounded degree, then does it isometrically embed in a finite product of trees? And apparently a few people asked this question. Apparently this was asked by, I wasn't here to hear any of these questions be asked, but I just read that they were asked. It was asked by Chapoy, Haglund, Niblo, and Segeev. They each asked independently if X is a cat-0 cube complex whose vertices have bounded degree, can X be isometrically embedded in a finite product of trees? Okay, and this question was answered in the negative by Victor Chapoy and Mark Hagen. They proved the following. They gave an example of a 5-dimensional cube complex that shows that the answer to this is no. So there is a 5-dimensional cat-0 cube complex whose vertices have degree at most 72. Call it X. And this X cannot be isometrically embedded in a finite product of trees. Okay, so this answered this question. So then they asked a follow-up question, which is this as small as you can do? Do you really need to go to 5 dimensions? Maybe there can be a lower dimensional example of such a cube complex. And yeah, so in some ongoing work with James Davies, we provide a smaller example. We show, in some sense, as small an example as you could wish for, really. There is a cat-0 square complex, so 2-dimensional. And the vertices in this cat-0 square complex have degree at most 5. And it still can't be isometrically embedded in a finite product of trees. And the construction of this thing is using some recent work of Davies and 6 collaborators that gives a new way of constructing triangle-free graphs with a large chromatic number. And what we do roughly is we realize those things as intersection patterns of boxes in the plane, and then we apply Segev's construction to the collection of partitions of the plane that you get from those boxes. So yeah, I'll stop there.